Hi, welcome to this webinar on fraud detection using the Oracle Autonomous Database and Oracle Machine Learning. My name is Charlie Berger. I'm the Senior Director of Product Management for Machine Learning, AI, and Cognitive Analytics here at Oracle. And you can reach me at charlie.berger@oracle.com or on Twitter at charliedatamine. And for the next 45 minutes or so, I'll talk about how to tackle the complex challenge of finding anomalies that may in fact actually be fraudulent behavior using the autonomous database and the built-in machine learning algorithms that are provided with that that are called Oracle Machine Learning. Oracle has a safe harbor statement that basically says the following is intended to outline our general product direction, and it's not intended for any commitments for any delivery of any material code or basically any futures that I might reference through the course of this presentation. So please refer to that. Thank you. So the goal that I have here is to really share some information on our machine learning algorithms that are embedded in the Oracle databases. Now, these algorithms are embedded in both the Oracle Enterprise Edition on-premise, and they're a priced option there, at least have been, and up on Autonomous Database, they've actually been included for free. So I'm going to focus a large part on the Autonomous Database because that's the exciting new area for us, but I'll also cover how to use the algorithms on-premise. And there's different the same algorithms, but sometimes different user interfaces or different points of APIs and such to access those. But I'll go through this and discuss specific use cases and examples and experiences and anecdotal stories and so on to try and make this hopefully interesting and of course useful for you, because finding anomalies and combating fraud is a very important area. If you'd like to, you can follow me on Twitter. Just follow me at charliedatamine, and I sometimes post different things out there, or information about the product, or technical updates, or webinars, or various things that I'm involved with, or sometimes just find interesting. So you're welcome to do that. Now, the first time I got involved talking about fraud, I was invited along with another fellow, Carl Rexer, actually from Rexer Analytics, to present at a fraud conference here in the Boston area. And I thought, well, Carl had done some more work in this area. This was 10 or 15 years ago, and I had not really spent a whole lot of time focusing on this. So I thought I better study up just a little bit. And I poked around a little bit on the internet and found, that there was this coalition against insurance fraud and a number of different societies of fraud examiners. And they had quite a mature industry solving and tackling fraudulent behaviors. And what was interesting was most of these people are also from a police or a military background, very investigators, things like that. But the information they had collated just blew me away. And I'll just discuss a few of these in the beginning here. That nearly one out of 10 Americans would actually commit insurance fraud if they knew they could get away with it. No shame, just I'll go commit fraud. Nearly 1 out of 4 Americans say it's okay to defraud insurers. I guess because they have so much money, we're just going to defraud them. And 1 in 10 people agree it's okay to submit claims for items that aren't lost or damaged, or for personal injuries that didn't occur. I guess they want to try and get their money back, or so their premiums or whatever they have to pay. 2 out of 5 people are not very likely or not likely at all to report someone who has ripped off an insurer. Nearly 3 out of 10 Americans, 29%, wouldn't report insurance scams committed by someone they know. That's the Progressive Insurance study. And about 35% say fraud cost their companies 5 to 10% of claim volume, and some say it costs more than 10 to 20%. And the good news, I guess, is detecting fraud before claims are paid and upgraded analytics were mentioned most often as the insurer's main fraud fighting priority. So that was kind of good news. And what was interesting, I go back a slide, was interesting, in one of the studies said that there was actually certain hotbeds of fraudulent behavior and car stealing and various kind of things. And it mentioned the town of Lawrence, Massachusetts. Well, it just so happened that I lived in Lawrence, Massachusetts for 2 or 3 years. And while I lived there, my car was stolen and my apartment was ransacked and robbed. So I guess the data is all true. So anyway, fraud is a bad thing, and crime in general is a bad thing. But they also had their approach to solve fraud. So they had this document called 20 Ways to Detect Fraud. And here's the first 6 of them. They said unusual behavior. Now remember, this is all coming from people, and you can see the links to where these documents came from at the bottom of the slide here. But they said most of these investigator kind of brains were saying, well, you'd have to watch the perpetrator, and they'd have unusual behavior. They may not even take a vacation or call in sick for fear of being caught. They may not assign out work even when overloaded. They have to do it all themselves. They may have increased drinking, smoking, defensiveness. There may be a lot of complaints, number two, about the action that's going on. There may be stale items in reconciliation. So in bank reconciliations, deposits or checks are not included in the reconciliation. That could indicate theft or fraud. Missing documents, excessive voids, excessive credit memos. And so, there's a bunch of, I'll call it business rules that were outlined here. And so it seems, well, maybe that's pretty easy, right? Well, it's actually a lot of work, and it's all required by humans, and the fraudsters actually are pretty smart, and they change their behavior constantly. So whatever you might think you're going to do to capture them today, well, they may have changed their behavior by tomorrow. So what I learned was this is pretty much a pretty big challenge. Now, what about machine learning? How can machine learning help here? Well, what is machine learning in the first place? Machine learning is really just using algorithms, step-by-step sort of procedures to walk through data and find patterns is one definition of algorithms. But algorithms that automatically sift through large amounts of data to discover hidden patterns, find new insights, and sometimes make predictions. Like, I think this is fraudulent. For a future prediction, you may just want to find out in the past what transactions were fraudulent, or you may want to catch it before it happens. So there's all sorts of different ways to deploy or operationalize a model. But in machine learning, there's a variety of different types of things you may do in the area of what's called supervised learning and unsupervised learning. Now, with fraud, if you have a lot of examples, you might be using something like supervised learning, because that says, I have a lot of examples of fraud or check fraud or tax fraud or whatever, insurance fraud, and I want to use these examples to train the algorithms. I have a lot of historical data, and I want to use the algorithms to differentiate examples of fraud and counter examples of not fraud. So that would be a supervised learning technique. There are also other techniques that would be more of an unsupervised learning technique, like the clustering or the specific anomaly detection algorithm that we also have. We have 30 plus algorithms inside the database that I'll get into in a minute. But these categories of algorithms for unsupervised learning are useful, because in those cases you say, I may not have a lot of examples, or I may not know what is fraudulent or not. I'd like the algorithms to sift through my massive amounts of data and sort of separate things out into different groups or clusters, or find those things that sort of stand out as being most dissimilar to the training population, and that would be specifically the anomaly detection, where the rate of fraud is maybe 2, 1, 0, point, some small amount of fraud. If you have 20 or 30% fraud or 5 or 10% fraud, you probably have enough examples that you can use a standard classification technique, like what I'm showing above. But if you don't, you might want to use some of these more unsupervised learning kind of techniques. And so, going on a little bit more on the concepts before we go into the details of the product. This slide or a concept I like quite a bit. I stole it, or borrowed it, I guess I should say, from some colleagues I used to work with, Michael Berry and Gordon Linoff, who have written some great books over the years. And they kind of use this example to show, well, let's say I have two different variables, income and customer months, and I'm trying to separate out, in this case, the lease churners, people that maybe buy a car and then come back and renew and buy another lease car from Toyota or Ford or somebody. And those people who say, no, I'm ready to, I'm done. I want to turn it in. I want to go elsewhere, or maybe not even get another car at all. And so if you fit a straight line equation or model through this, like a regression, just a simple linear regression, it doesn't really find a good separation between the blue loyal customers and the red lease churners. But if you add a little bit more complexity to the equation and do more of a quadratic or a cubic or a multivariate type of model with more complex terms in it, I guess I'd say, then notice it picks up a few more of the blue guys down here and sort of carves things out just a little bit more intelligently, but it's still not doing a very good job. If you apply machine learning techniques, they're going to, in a systematic way, sort of walk through all this data, find sort of the curves in the data, the pivot points and such, and a decision tree would carve through this data almost like butter and find all those different patterns. And the nice thing about decision trees, is that at the end of the day in a decision tree, it'll give you the reasons why. So it'll say if customer months comes up to some certain number, like it's greater than 14, and income's less than a certain number, like say $90,000, then I have found as an algorithm, I found that 1, 2, 3, 4, 8 out of 8 of these people, in fact, all churn. So I have a very strong signal going on here. And the supports, so I'm 100% confident if I find somebody else that looks like this, of that behavior. And the support means how many of these in the whole population. So if you add them up, there's 39 little people here, and 8 of them fit into that little segment. Here's another one where I'm a little bit less confident. I'm 83% confident, and the support is 6 out of 39. And it's a slightly different rule, but this is what's called supervised learning. I'm using a decision tree technique, and the nice thing is I have lots and lots of examples on which to train. And so I can find insights, I can actually make pretty good predictions based on this. But what happens in the case where I have very few examples, or I don't even know what the examples are? So here I've switched the scenario just a little bit, and I'm saying, well, now we have normal customers in blue, and I have a lot of normal customers, and then I have just a couple of guys that I've noticed are doing cell phone fraud. They're doing something with their cell phones that's not good. They're not paying their bills. They're making phone calls that haven't been approved or paid for. They're somehow spoofing the system in certain ways that I don't like and I don't think is good behavior. And I'd like to try and find these guys. Well, how do I do that here? It's a little bit tougher when I don't have enough examples to train. So in the previous one, I had a lot of examples. The algorithms can say, well, here's examples of A, here's examples of B, and I can kind of learn the differentiation here. Here, I only have 2 examples, or maybe fewer than that. So a very small amount. It makes it hard to differentiate those 2 different things. So what do? Well, I think of our good friend Waldo. I don't know if this is across all countries and all cultures, but Waldo was a fairly popular thing when my kids were smaller, and they'd have these big picture books with these complex scenes of all these different people doing things. And the challenge was, can you find Waldo in that crowded scene of all this activity? Could you find Waldo? And so we're going to play that game here right now. Can you find Waldo in 10 seconds? So we're going to show a little crowd here. We're going to ask you to kind of just visually see if you can find him. Ready, set, go. Now there's the crowd, and I don't know if you can find Waldo, but time's up. There he is. So there's Waldo. Now, how did I find Waldo? I didn't find him, and I kind of cheated and said, well, there he is, and I circled him when I had more time. But how does your brain find that? Well, you're looking maybe for these little striped things like here, because you know Waldo has a striped shirt, but you also see other people's striped shirts, like over here, and over there there's a blue striped shirt. There's a little kid with a striped shirt over here. You know, he has this silly little hat and he has these glasses. Well, there's other people with silly little hats and glasses around here too. So what you're really trying to do is not only find pattern matching, but also find things that sort of stand out. And the brain has an interesting way of sort of sifting through this as fast as it can. And what the machine learning algorithms do is try to replicate some of that logic as quickly as it can using the power of computers and large amounts of data that you can feed those computers and algorithms. So that's what we've done in the Oracle database. We've added in 30 plus of these different types of algorithms, and anomaly detection is just one of those, but they can all be used in combination or in isolation. So if you're doing this and you're looking for Waldo, well, there's a lot of other more interesting use cases than finding Waldo. There's financial fraud, like maybe transactions. There's medical fraud. There's prescription fraud. There's insurance fraud. There's all sorts of costly challenges there. Just finding anomalies or rare events or bad guys, whatever bad guys means to you. So here's one of my favorite stories. It's the UK National Healthcare Service. And I've worked with a little bit with these people. They've done great work. Nina Monkton, Peter Barker, Abby Hay, who used to work there, and a number of different people. So they have been using the Oracle Exadatabase, and they've been analyzing their data. And they have said that the costs of fraud is over $1 billion a year. Now they've actually identified $1 billion of potential fraud, and I think it's up to something like 450 or $500 million of Great British pounds of fraud that they've actually confirmed. This is fraud. Have they done that? They've been using the analytics that come with the Oracle database and the machine learning techniques to sift through that data and find things that sort of stand out. Now, how do they go about doing this? Well, I don't want to get too simple on you, but it's kind of like the old Big Bird song, right? And if you remember his song, you'd see, and if you click on this, it'll play a little video, but I'm not going to do it right now. But if you look at this, you see Big Bird, and he's got 4 different bowls of bird seed in front of him. And he kind of says, which one of these things is not like the others? One of these things doesn't belong. Can you tell which thing is not like the others before, by the time I finish my song? And he kind of then stops and he says, well, this bowl over here is bigger, and that kind of stands out. So that bowl must be different. And it's a fun little thing, but that's what we do with the algorithms. And so if you think of that from an algorithmic and a data point of view, you say, well, here's a bunch of data that I have. I have a cluster of data on x1, x2, x3, x4, a bunch of different dimensions here. So I'm looking at them all, and I may have lots and lots of data, very few examples of what I'm looking for, many, many attributes. For any one single attribute, a value may seem okay. Like let's say x1, which may be age, income, the amount of the claim, the number of claims, the time between claims, and it may be a number that seems kind of fine here. The next variable, that one's kind of fine. This one may be a little bit sort of on the lower, level of this categorical or varchar kind of variable here, and this one may be a little bit on the high or whatever. But each one taken unto themselves doesn't seem quite that unusual. But maybe if you take them in collective, from a collective point of view, and look at sort of things that are different in a multidimensional, multi-peculiar kind of way, you might find, well, really, this is one that's high on everything, or maybe it's dead center right down the middle. It's too normal. It looks like too perfect, if you will. So what we do is we train on a pile of data, a haystack of data. We're looking for the needles, but how do we find the needles? We train on what we are told is normal data, and we apply that model of normalcy, if you will, what we think is normal, to the same or a new set of data. But it's nice to train on your starting set of data first, because now you're looking for what's different. You sort the records in how they are most dissimilar to the rest of the training population. And if you find things that you say, yeah, this record here pops to the top of the list, and this one stands out, then you say, well, is this valid or not? Now, if it's a valid record, maybe you want to pull it out of the training population. I mean, it's a valid fraud. It actually is confirmed fraud. Maybe you want to pull it out of the training population and rebuild the model and train again. And you kind of iterate through this process, maybe sifting through the top 1, 2, 5% of the records that are flagged as being suspicious or at least anomalous from the training population. And as you give it an ever more pure training population, then you get an ever better, more accurate model. And if you have enough examples of what you're looking for, that you find, okay, here's, check fraud for this type of check fraud, or insurance fraud for, rain damage or flood damage, and, and the person lives on a high hill or whatever. Maybe if you have enough of these examples, you can set them aside and use those as a training population for doing what we were talking about before, the more supervised learning classification kind of technique. So there's a methodology here that can kind of start out simple and get a little bit more complicated and have a feedback loop, which is what I'm trying to say here. Now, before I go into too much of the product, I want to give you another example, and this is a little bit more like a real-world example, and this is actually my own credit card from a while back. And if you look at this, I don't know if you'll see the fraud while I'm kind of talking right now, but the first thing a lot of people say is, did you really go to Monaco? And the answer is I did. I did go to Monaco. It was actually a business trip, and I had a great time. And I did have a bottle of wine there that I charged to Oracle. It was lovely. Actually, this is my own personal credit card, so I did not charge that to Oracle. But I did, right? And then I go a little bit further here, and I say, well, gas stations. Those are a lot of gas stations. I'm buying a lot of gas for some reason, but I'm buying gas. The other thing, if you looked at the geospatial point of view of this, the mobile mart where I'm supposedly buying all this gas is actually in an area of northeastern Connecticut that I live outside of Boston. I had not been to that part of northeastern Connecticut for years, and it's just struck me as suddenly I'm getting charged all these charges from gas in that area. They're all $75. That's kind of weird too, right? $75. I always pump $75 worth of gas, or I go in there and buy maybe some items, and they add up to $75 exactly, 00 every single time. That seems a little unusual. And if you've picked up on the date and timestamp by now, they're all in pairs of 1 minute apart, 2:05, 2:06, 11:48, 11:49, and so on. that's a little unusual too. And if you used something like the SQL windowing functions, and I'm kind of heading in a direction here for how you would solve a problem, notice there's a lot of domain experience here that has really little to do with the machine learning algorithms. It deals a lot more with the domain expertise and maybe the data professionals and the Oracle SQL people that know how to calculate and derive these what I'm going to call engineered features. But if you did the SQL windowing functions and you compared the amount of purchases that I would do at these gas stations or in restaurants or whatever, and had windows of time, you could say, well, here's how much he typically pays for gas per month, and now more recently he's paying this amount. I could derive some very clever, what we call engineered features, as clever inputs to the machine learning algorithms to try and capture and find this fraudulent behavior. So this is a typical example of how you tackle or solve a fraud problem. And it leads into this other statement by Albert Einstein that I always like to refer to because I think it's so appropriate. And especially if you're an aspiring data scientist, you're an Oracle technical professional, and you would like to leverage all these powerful algorithms that we've put inside the database, the very first, most important thing is to start with a business problem statement. And what Albert said was, if he was asked to solve a problem in an hour, then he would spend 55 minutes thinking about the problem definition. What is the problem we're trying to solve, and then just 5 minutes about the solution. So the example I use here is if Albert's asked to save the planet, then how we would go about saving the planet? Well, the first question is, well, what do you mean by saving the planet? Do you mean every man, woman, and child, or all the trees and animals and fishes, or all the people and the animals and the trees, or just the children, or just the women and the children, or just the dogs and cats? And so each one of those very specific. And for how long? Do you want to save them for 5 minutes while maybe a meteorite goes by, or do you want to save them for the next 100 years? So each of these problem statements are kind of important to think about, and then once you define what is a good problem statement, then you can start thinking about the solution and what data you would need from a machine learning point of view and so on. So I just like to point that out because so many people talk about machine learning. I need to have a data scientist come in here and solve all my problems with Python or R or whatever. And we integrate and we support Python and R and all. But I do want to encourage you as an Oracle professional that a lot of this stuff is in your wheelhouse. This is the kind of stuff you already know your data, you already know your business problems, and I'm here to kind of help you along to kind of show you how you can also now use all these algorithms to solve problems. So I wanted to just quickly, before I go into the product, just touch upon very quickly some customer successes. We do have customers that have used the product and solved some things, and some of these are the ones I'm showing are public ones that have come out and said things publicly. The biggest one is the UK National Healthcare System. Every time I talk to these people or work with them, the numbers keep on going up higher and higher. But they've been using the Exadata. They've been moving everything up to the cloud. They use our machine learning that's in the database. And they've just been, they started out with a data lab of, I think it was one data scientist and one part-time DBA, and they've just grown it up to, 10 or more people over there now. And they've been quite successful, and they just have huge amounts of expenses with healthcare. The entire citizenship of the UK has nationalized healthcare, and all that data about their billing and medical billing and everything and medical data is in an Oracle database. So they've just kind of whacking at this using these algorithms and Oracle Analytics Cloud and so on, and they've had some great results. Fiserv was a company I'd worked with a long time ago that really were the first to really kind of point out a few of these things that were so important to them. And they would say using SAS, which is another commercial, what I'd call sort of a legacy machine learning statistical product where you take the data out of the database and you bring it to a specialized platform to analyze the data. And so it's taken 3 months to build and deploy a model with SAS because they had to take the data out, they had to move it, they had to vet the model and get it all going, and then they had to operationalize that model. And the way they would operationalize it is to kind of take the logic of the model, the if-then statements and so on, the coefficients, and re-implement that as basically scripts, SQL scripts. And they got it down to a day just by running and building the scripts and inside the database. So it's a very good story. Turkcell, similar kind of thing. They would have a phone card fraud. People would use these phone cards, they'd go off and make a very small charge to their phone card, and then if that got through, they'd run off and charge some bigger things. And so you wanted to stop it as quickly as possible, and they got it down to 4 hours. It was pretty fast. StubHub uses our machine learning. If I say, hey, I have tickets to the Patriots, they're playing the Super Bowl again, and I have tickets on the 50-yard line, and I want to sell these, they first, before they allow me to sell them, they kind of go off and say, okay, who's this guy, Charlie Berger, and has he ever sold tickets of this value before, and what's the likelihood that his tickets that he's trying to sell or resell on our market are valid, and they kind of give it assign a probability to that. And they actually use the integration with R also to do some specialized call-outs there for that. So it's a very clever use case. Guarantee Bank, a bank in Turkey that uses a number of the Oracle products, and they're doing ATM fraud, detect fraud. StubHub, I guess that's a repeat actually. Zagra Bank, a bank in Croatia that I spoke with these guys at Oracle World before, and they were doing fraud. They were also predicting customers who are likely to be high-value customers for buying certain products. So they just moved everything into the database and started analyzing the data there. And their mission was also to sort of wean themselves off of using other commercial machine learning and statistical analysis products. So enough with that. Let's go into the product and how we're going to solve some problems. It's called Oracle Machine Learning. You may have heard of it over the years as being called Oracle Advanced Analytics, Oracle Data Mining, Oracle R Enterprise, Oracle Data Miner, Oracle R Advanced Analytics for Hadoop, and so on. We've sort of consolidated all that into a much more sensible naming scheme, and we call everything now Oracle Machine Learning. On the autonomous database, we have the Oracle Machine Learning notebooks, which sort of started that whole sort of trend, and we've just renamed everything OML for SQL, OML for R, OML for Python, which is coming soon, and so on. We also have the new Oracle Machine Learning microservices. There is a whole other topic. There's a fascinating area there as well. So the whole offering, and these are just embedded in the database. All the database, the OML for SQL, R, and Python, Oracle Data Miner, and the notebooks are just in database implementations of algorithms. And like I said, there's a library of 30 plus algorithms. You can do a lot with that. So each of these algorithms are in database implementations. We started out with the naive Bayes algorithm years ago, because naive Bayes, if you remember that algorithm, is just based on conditional probabilities and counting. That's how you do it. You count things. The database screens through data. You can count things very, very quickly. And so if you just ask the database to count everything and build a conditional probability model based on that, well, that's the beginning of one of the easiest algorithms that we've been able to implement in the database. And over the years, we've added some much more sophisticated algorithms like neural networks and support vector machines and random forests, and we have XGBoost is going to in release 20 and so on. So there are quite a few algorithms that we support. In the fine print, you'll see that we also support partitioned models, transactional data, unstructured data. So these machine learning functions sit as pure functionality to all the rest of the functionality inside the database. So I always joke that if marital status is actually a field that's not single, married, divorced, or whatever, but it's something like a prenuptial agreement, or it's a paragraph, or it's a bunch of tweets, or an email, or maybe a police report, or whatever. Oracle Text can search through all that, tokenize all that data, and serve us up a vector of words, and we count the frequency of those words compared to the population frequency, the frequency of those words in this one record versus the population frequency, and we use that as just another input. Similarly, if you have transactional data, we can do the same sort of thing. You don't have to explode out a column for every single, let's say, drug that you're taking for the national health system. You wouldn't store the data in the database that way. All the transactional data would be stored as transactional tables, and what we do is we join that table, and then we aggregate those transactions, and we feed that into as a complex star schema object into the algorithms, and that's the way we're able to digest that kind of data and find patterns. It makes a lot more sense when you bring the algorithms to the database. It just opens up so many doors and new possibilities. We also have quite a few statistical functions, and t-test, f-test, all the basic building blocks of statistical functions are also in the database. So if you take this whole toolkit of analytical functionality and you say, well, I'm going to now bring it over to a potentially fraud or anomaly kind of problem, you can come to that problem with a lot of horsepower, analytical horsepower. So here's just a few more quick slides that talk about the specifics of how this works. Let's say I'm going to try and do some statistical analysis, just looking at the amount that men buy versus women buy, and group that by income level and see if I can find any statistically significantly different groups. And in fact, I can, if you remember from your stats classes, anything less smaller than a 0.05 means it is statistically significant, and I can kind of do that. It's just a SQL query. So that's the way it works. It's just a SQL function. Similarly, if I want to do a classification model, well, it's the same kind of syntax. It's begin DBMS data mining create model. The model name is by insurance. I'm doing a classification rather than a regression or other types of functions. So the data table name, materialized view, table, whatever, is customer insurance lifetime value. That's the unique identifier, customer ID. Target column is by insurance. And I have a settings table, which would be like auto data preparation and the algorithm settings. So that's all I do to build the model. And when I want to apply the model just says, I decide to select prediction probability using that model, predicting the outcome, yes, and I can even use from dual. So if I have some sort of real-time, system where people are, scanning things on a barcode system or entering things on an ATM, I can get a real-time prediction, and I don't have to, like in legacy systems, move all the data out to a separate analytical server. So especially when you're trying to do something as important as fraud, having this real-time model apply or batch apply, however you want to do it, it's just a more efficient, fewer moving parts kind of mousetrap. If I want to do another technique called attribute importance, just find me the key attributes here that are related with a particular outcome. Did they buy insurance, yes or no? And what are the variables that are most influential or important? That's the way that works. So you can kind of see the pattern here. But if you say, hey, I don't speak SQL so much, I'm really a data scientist and I speak R. Well, what we do is we expose those same algorithms and we wrap and integrate those algorithms and expose them to other languages. Here we are showing how that works with R. And notice that it's just R syntax, but I'm getting the same results. So over here I got 0.2161, here I got 0.2161, and so on. It's like Google Translate, right? I speak one language, but it translates it to the other, and I'm leveraging those 30 plus being database machine learning algorithms. And what's coming very soon is we're also integrating with Python, so I can now speak the Python language and call those same functions. Now in both the R and in the Python, that's one thing, but we also integrate with those languages. So if you want to make a call out to some Python or R package, you can do that, and you can use any of those packages on-premise. On the cloud, in Autonomous, it's a little bit more locked down, or will be when that's available, early 2020. But here, if you're on-premise and you're making a call, you do pay a price. There's a little bit of a trade-off, because you say, I don't want to use those 30 techniques in the database. So you need to use something sort of special. So in that case, what I do is I have the database do a remote procedural call, or using XProc. It sends that data out to the R server, in the R example here, and it makes a call out to that, and has the R package do its math, and then return a value, and you can save those scripts in the database, and you can sort of use it for almost, what I call analytical duct tape. Now, if everything you were trying to do was all in open source R or Python packages that we did not have equivalents for in the database, I would say, well, maybe that doesn't make a whole lot of sense to use Oracle. But if 80, 90% of what you're trying to do is all in the database, using the techniques that we have available here, and you can solve all your problems, and you just don't make exceptions or doing certain custom things, or maybe the prototype, then I think it makes perfect sense to go that route. So we have a whole family of offerings now. We have the notebooks that I'll go into in a little bit more detail. We have the drag and drop Oracle Data Miner GUI that comes with SQL Developer, and we have the RStudio on premise. The notebooks will be enhanced to support both Python and R. The Python, we keep on saying it's coming soon because it's in early 2020. And what's nice about it is if you transform the database into an analytical platform, it opens up the door to more easily develop applications. So that's, I think, what the really exciting part is. So more and more Oracle is trying to not only manage your data, but also analyze your data. And what's nice in this scenario, which is also particularly important in fraud, is sometimes you have lots of data that might be coming in into your data lakes. It might be coming into Hadoop or Spark or various other areas as well. And that may be where all the data is. We have algorithms that run over there, as I talked about before, Oracle Machine Learning for Spark. But I think lots of times to solve a problem, you need the combination of the variables or the attributes that are in the database, like gender and age and previous transactions, joined with some new data that may be tweaks or geolocations and things like that. And I think this other data, oftentimes it just makes sense to boil that data down, boil down the data lake and come up with counts, totals, changes over time of this data, join it to the rest of the data, and then just keep on going and do finish your methodology perhaps in the database. So what's nice about bringing the algorithms to the database is if you have complicated kind of problems like this one here, that I'll show you in a second, we have a lot of horsepower in the database to solve these kind of things. So if I have geospatial locations and Charlie is driving around this rental car all over the place, I got a Hertz or an Avis or some sort of rental car, maybe they want to say, hey, what's he doing in this part of town? That's kind of a dangerous part of town, or a lot of potholes are there, or he didn't say he was going to take it over the state border or whatever. That's not valid. I have the geospatial data that can come in, and I can calculate, say, the percentage of time spent in various things, or how many exceptions did he have, how many infractions did he have. I also have the graph database capabilities in the database, where I may say sort of like, 7 degrees of Kevin Bacon, how many transactions or relationships has Charlie had with people on, let's say, my bad list of people that, we don't want him to talk to those people, they're bad people. I also have, I can create a whole 360-degree view by joining various different sources of data, including unstructured data like tweet and blog posts. Along with my customer data, I get a very complex view. I can build predictive models. I can apply the results, leave it on the database, and I can kind of look for at-risk rental customers or fraudulent transactions or whatever. But using richer, multi-sourced kind of sets of data. Now I do need to sort of host all this data at some point in one place. I can't. I can do a federated query, but I can't yet do a federated algorithm. I have to kind of bring all the data together to have the algorithm consider all that data to build a model. Now, a couple more things here, I think, before I move into the real details. Here's a report from Fern Halper that asked, I think, the best question. How long does it take to put a defined model? In other words, I built a model for fraud, and kind of like some of the other examples I gave. Now I want to operationalize it. Well, this is, kind of significant. 3 months to 9 months or more. That's something like 65% of the population. So that's really, really long time. Now, this is Fern's study. I don't want to imply that the next slide build is from her. This is from me now. But my point of view on this is, well, they must be using products like that or open sources or other commercial products, because they're schlepping the data back and forth. They're using sort of legacy approaches. And if they use the Oracle in-database algorithms, it couldn't take that long. It's just you're building the models and applying the models just as SQL functions, whether or not you're using R, notebooks, Python that's coming, or whatever. You're just using functions inside the database that are massively parallelized, and you're just running scripts and build models, apply models, and off you go. So let's move into how we approach detecting fraud. And we're going to use the autonomous database and Oracle machine learning. So we're going to go into this and talk about Oracle machine learning, which is the new notebooks. So they're Zeppelin-based notebooks. They're a collaborative user interface for data scientists. It comes packaged with the autonomous database. And we expose all the currently only so far the SQL algorithms. So you notice the R or the Python integration here. I had to remove that because that's coming soon in 2020, early 2020. It's not quite here yet. But we have the 95% or almost 100% of the same algorithms. We just can't use those other languages yet. But again, as I'm saying, that's coming. So with the Oracle Autonomous Database and Oracle Machine Learning, we provide a number of different example notebooks. And I'm going to go into a specific one for anomaly detection, but for insurance claim data. But you can use these notebooks as starting templates and just change some of the data tables and change things around a little bit and apply them to your own data. That's very good sort of starting points. So the one that I'm going to walk through right now is one I've created that's not one of the example ones. It's slightly different. But I'm looking for automobile insurance claims. And we talked about how many people are comfortable doing fraud, and we want to kind of stop this. So we have this insurance claim notebook. In the notebooks, you can put in little pictures in here. You can add some markdown language text. You can have hyperlinks. You can set up a lot of things here. And then each little paragraph I click run, and it's going to run that paragraph. So here, click run. Here, click run. And I can also collaborate with other people. So I may have 3, 5, 10 of us all working in the same notebook trying to solve problems. And that's one of the beauties of this ability to sort of collaborate all up in the autonomous database. But so here we're going to look at the automobile insurance claims data. We have data a week of the month was fraud found. So here we have some supervised, some labeled data that we say, yes, we found fraud, or at least we think we found fraud. It depends on how you want to interpret that. Is confirmed fraud, or maybe we think we found fraud, we'd like to still just use that as another input variable along with everything else here. We have the vehicle price, we have a number of things. And we might start to graph that data. So I just take this table, on any of these tables, if I click pie chart, bar chart, whatever, the nice thing about the notebooks will give you some basic graphing capabilities. So we see that, more accidents seem to happen on Fridays and Mondays. Where the accidents happen, they're mostly in urban areas rather than rural. I have the age of the policyholder, in different sort of scatter plot, different visualizations of things. Now, if I could solve all my problems using just a few pie charts and bar charts, it wouldn't be really sort of worthy of machine learning here. So, of course, it's a little bit more complicated. I can look at graph after graph after graph here, but I still haven't really found where are the fraudulent claims, what are the patterns that I'm noticing here. So I'm showing some nice, useful, pretty graphs, but I really haven't solved anything yet. So now we're going to go off and build a model. Now, if I'm using the GUI, that I'm going to show you later on, we actually have some other stuff called AutoML, user interface and AutoML that's coming along. We talked about that in Oracle Open World. So you don't have to always write code, but underneath the GUI is code, right? So underneath the GUI, I'm doing these things where I'm building a model, I'm dropping the model settings, I'm dropping any previous model, I'm creating a model settings table, and I'm going to build the model here. So that's kind of what I'm doing. Now once I've built it, so that's all it is really, right? I'm building the model of one class supported vector machine. That's like that code I showed you before. So it's very straightforward. And then when I want to display the customers and apply it, I can just say, well, show me apply this model to my customers. And then I can sort these if I want, sort them in probability of fraud. And I can kind of take a look at each one of these records and see, hey, what's going on here? Maybe I should pull this 26 to 30-year-old female in and say, why, what's going on here? Now, the rest of the things that I'm not sliding over here is she ended up having a Honda Accord that she claimed was worth more than $69,000, and that strikes me as a little bit unusual. So I can kind of sift through this, look at some other different graphs, and figure out various things. Display all customers and probably be anomalous. Display all customers in another way. Display all customers with one vehicle, two vehicle in the accident. So these are all the things that I've predicted about a certain probability of likelihood of fraudulent that I'm now able to kind of drill through and see them in different ways, right? So I think that at a certain point you reach this diminishing return when you say, now that I've assigned a probability to this and I want to investigate this further, maybe what I want to do is go over to Oracle Analytics Cloud and take a look at these resulting predictions and tables and visualize it on a map, visualize it in a lot of different ways that I could use other tools. So I'm using the machine learning in the database to do the hard, heavy lifting in machine learning, but then I'm maybe continue on and look at the results somewhere else. So that's a quick look at what we do on Autonomous with the new notebooks. I thought because so many people also have on-premise or have SQL Developer and maybe are not using this, it might be appropriate to kind of show other ways that we also support for solving these problems. So here's a slightly different story to make it a little bit more interesting. Here's a tax non-compliant audit selection. So which tax submissions should I set aside in audit because I think they stand out, they look kind of weird. So here I can do a one-class support vector machine model using unsupervised learning. That's the one right here. Or I could use classification models where I say, well, I have a lot of examples to train on. So what I've done here is just done both ways. But what's also nice is I have a drag and drop GUI that comes with SQL Developer. So it's just an extension to SQL Developer, and I can just sort of drag and drop these data nodes, these model build nodes, and here I'm training up the normal records, and then I'm applying them and sorting them with a likelihood to be different. And here I'm also, they're anomalous, the value is target field is 0, but I can also see what are the variables that sort of most contributed to my thinking, this was perhaps anomalous in all these different records. It looks like witnesses present, no. The policy claim was more than 30 days. The agent type was some sort of external type, and these are the variables that sort of left out the most. But my point is I don't have to define business rules. I can let the algorithms in the database walk over the data that's in the database, find these patterns, and serve up these predictions. So when I query my database for pretty much anything I'm curious about, I could have the actual value, and I could have a predicted value and a probability of that predicted value. So here I've dragged and dropped my data source over here. I can then view the data, and there's the data. Is it compliant? Yes or no? That means, is the IRS, do they think it's okay or not? I have the adjusted tax, the itemized deductions. I have a bunch of different data here. And one of the first things I may want to do is drag and drop an explore node over here and visualize this data, which is what I'm doing now. So I can kind of click on each of these different thumbnail histograms, which is what I was doing in the notebooks, but here I have a slightly different user interface on premise. Now the notebooks will add something a little bit like this. It's going to be a code-free way of doing much of the same thing, but it's not going to be the same drag and drop, and that will be called the AutoML user interface. But here I have the sort of fat client on-premise version of doing this. So now I can run this. This is a filter column node that's actually also doing this attribute importance. So it's counting the number of nulls, the percent uniques, the number of constants, and it's kind of telling the rank of how important these variables are. And again, these are the variables that came out as the most influential on determining, in this case, in a supervised learning technique, saying, are you fraudulent, are you compliant, yes or no? Now, as I said before, depending on your use case, you could be using classification, you could be using unsupervised learning techniques, and so on. Here we are doing, right there, we are doing the supervised learning. Here we're going to kind of switch over to anomaly detection model, and we're saying we're looking for all the factors most associated with anomalous records, and the model has found these factors, which, if you think about all the different variables and all the different values, like, the number of mortgages 2, the number of mortgages 1, the marital status married, this is a lot of data and a lot of permutations, but it's kind of, trivial for a machine learning algorithm. The algorithms kind of sift through all this stuff, and they can find these very complex patterns, codify them all together as a quick model, and then I can use that model to apply it to additional data, either in real time or batch and make predictions. So that's what I'm going to do here. I'm going to take the data and I'm going to apply it to some new tax submissions and make predictions. And I give the predictions, and I can have a probability of them being anomalous. I can also have these little sort of pop-up rules, what we call prediction details, that we also infer from the data. And we'll say, well, this record is suspicious because the monthly overdrawn was a minus 123, which seemed weird to us. The marital status was widowed, which seemed a little weird to us in North Carolina and so on. So it may not be like a smoking gun. It's a little bit of a hint as to why the algorithm pulled that record aside. Now, in this case, we're going to switch gears a little bit. We're going to say we're doing a classification technique. So we're trying to find, using examples that we have labeled data. This is fraudulent, this is not. It's a little bit of an easier case here. We're going to use a decision tree. And the nice thing about a decision tree is I can find, notice the red versus the green. Here's all green over here. I can find if, that I'm 56% confident that represents less than 1% of the total population here. You kind of see where the pockets of different sort of patterns have been uncovered, and I can use this to make predictions. So this is just one of the many 30-something algorithms that we have inside the database these days. And the nice thing about this user interface also is, in the notebooks I was writing the scripts. Here I'm using the GUI to generate the solution, but I can also generate the code from this GUI. And again, on the cloud, the AutoML user interface will do the same sort of thing. Once I use this sort of wizard-driven click user interface there that's coming, we previewed that at Oracle Open World. If you look at the Oracle Open World presentations that are posted in the blog, you'll see that. But we also then generate the code, so it's sort of an accelerator going to deployment. So what's that doing under the hood? When I run this little anomaly section node right here, what that really is doing under the hood is this begin DBMS data mining, claims model classification. The target field is null because I'm doing unsupervised learning. I can apply the model here, maybe where some other conditions hold true. Past number of claims is 2 to 4 or more than 4. And I can just apply these predictions and leave them as a table in the database and maybe serve them up in a GUI or in Analytics cloud or part of an application. If I want to systemize this thing and make it an application, I can just say, set it all up to just run every so often. Or set up a trigger, whatever I want to do. So, as I've been kind of covering, there's a number of different ways you can solve or attempt to tackle fraud and anomaly detection. I've shown a few of them here. I can just use the one class support vector machine, right, where I have some data and I'm trying to find, say this is normal data. I want to apply a model to it and find the things that stand out as being dissimilar to the trained population. In the classification, it's like I have a lot of examples. So I have examples of good and bad, or bad and good, or whatever, and I'm using a whole different kind of approach. In clustering, I'm saying, well, it's sometimes useful just to try and say, well, I don't even know what I'm looking for, but just you find, in an unsupervised learning kind of way, algorithm, can you find these natural subpopulations of people that are mostly this or mostly that or whatever. And then I have another record. What people do is they say, well, Charlie, he's not exactly a soccer mom, and he's not actually a baseball dad, and he's not exactly a internet banker, but he's not exactly a paper banker either. So he stands out as being a little bit different, and that sort of raises some suspicion. Now you could take combinations of these, right? Do the clustering, and then push the clustering through either number 1 or number 2, right? That's kind of a very sophisticated way of doing things, and that's what what we recommend that you do. Now that we've turned the database into an analytical database, an AI intelligent database, if you will, whatever you want to call it, it's a lot easier for you to leave your data in the database, safe, secure, encrypted, parallelized, backed up, audited. But now we bring the algorithms to the data. We don't move the data. Now you can assemble these pretty cool methodologies. The last one's sort of all the above, right? A panel of experts. 5 out of 7 models think that maybe you're doing something unusual here. Let's pull Charlie Berger over and have a conversation with him. So here's kind of an example of that from the user interface. I'm using a simple model, simple fraud detection here, and here I'm doing a more sophisticated fraud detection where I'm doing the clustering and assign the clusters, and then out of each cluster I build separate anomaly detection models there. It's a little bit more tailored, a little bit more sophisticated. You can set up feedback loops. You can imagine doing a lot of clever things. And this is, as I said before, capable of also handling the unstructured data, the transactional data, the geospatial data, the graph data, and so on. A couple more things before I close up. One of the things that I think is most powerful of everything you're doing here with machine learning is to use your domain knowledge. So you as a SQL professional, probably you're an R professional or a Python professional or whatever, but you want to use your domain knowledge to tease the information closer to the surface of the data. So you may have used the SQL read and lag functions. You say, well, I've noticed rate of change. I know a guy that was doing check fraud. He'd say the check fraudsters would set up establish a certain amount of a relationship with a bank and write a certain number of checks each month, and the amount of the checks and so on. And he would have a SQL windowing function to check and capture that for the last 6-month average, and then another SQL windowing function that for exactly the same things would do it for the last 24 hours, and then he would compare those two, and those comparisons were very powerful inputs into whether or not it was flagged as potentially fraudulent or not. Reporting totals in comparison to the population average. So the UK National Healthcare was doing things like, well, the number of opioids Charlie is getting versus, say, the population average. And if I have 400 opioids after surgery and everyone else gets only 4, then I have a derived variable of engineered features, what we call it, of 100 times. And that's a pretty interesting input variable. So a lot of different things here that you can do to derive engineered features. And if you look at how you do this today, a lot of times this is using SQL. Now you can also use the R to do the same things, and it'll push it down to equivalent SQL, so you don't have to move the data out. And as I said a few times, we're also supporting Python, so you can speak, for standard transformations like this, you'd use Python and have it pushed down for in-database execution. And here's that SQL pattern, so the number of dropped calls and so on. It's a little bit of a whole topic unto itself, but the database has some clever, powerful functionality that I view as just inputs to then the machine learning. And here we're doing looking for dropped calls, spikes, and things like that. Maybe indication of fraudulent, maybe indication of likely to churn, whatever you're trying to do. But the key is you're deriving clever input variables using the power of the database. And remember that model that we did with the decision tree. Well, I would never show this to the manager or my boss. It's just way too complicated, right? I mean, I have this whole complicated thing here, and I say, hey, look at these results. So what do? I leave the results in the database. I call up something more appropriate like Oracle Analytics Cloud, Oracle Data Visualization, and I say that same attribute importance that I was showing before, well, here it is in a nice, well-behaved, beautiful graph, and I can share this using a whole different sort of more appropriate user interface here, but I'm using the database as the common hub where all this is happening. And similar to that decision tree I was showing you before, awfully complicated, but if I push that out and then view that in a different point of view as a pie chart where each of these different slices of the pie is a rule of the description of these different people, that seems like a much more appropriate, much more digestible way to view those results. So, a much better way. And what I'm trying to point out is the combination of these all Oracle products all working together just has fewer moving parts, and you can do so much more easily the same thing. So in sort of summary, thank you for your time, but I also wanted to call your attention to an annual gathering that we do, which is the Analytics and Data Summit. The next one will be February 25th through 27th. It'll be out in California. That's the old Sun campus out there in I think it's Santa Clara. And we'll have 3 days of people giving talks like this. We'll have hands-on labs. It's very inexpensive. It's like under $500 to go for the 3 days, which barely covers your cost of meals and such. And we'll get about 500 people out there again, hopefully. And I really encourage you to, register early. The call for speakers is already out, so and if you want to submit something, please do it right away. We also have these tech casts that are every 2 weeks. We run some tech casts, so I encourage you to, think about submitting something there. And I wanted to thank you for your time listening to this webinar. Hope you got something out of it. If you want to follow up and reach me, it's just charlie.berger@oracle.com. And as I said before, you can follow me on Twitter if you're so inclined. Again, I wish you all the best using our algorithms that we put inside the database now, and I wish you all the very, very best and good luck. And thank you for listening to this. Thank you.